differential equation on cooling. Whenever I teach differential equations, I always put in a question on Newton's law of cooling. I think it's really interesting. So I've got the advantage of having seen this before or something similar. But in any case, let's just go with it and set up what's going on. So part A, actually, I don't normally consider this, so this is new for me. We've got temperature as theta, and when it's removed from the oven, it's temperature. So that's going to be when time is 0. The temperature theta is going to be 160. And then we're working in minutes. So when t is equal to 10, we've got theta is 125. In the first scenario, we're assuming that the rate of decrease is constant. So actually we could draw a graph of what's going on. And we've got the starting temperature, and then it's just going down the straight line like this. Starting, you don't necessarily have to draw this graph, but yeah, I'm gonna get a straight line model. I can immediately see that. You could even probably you could use the coordinates to just write the straight line down straight away, the equation. But we're going to follow through on what the question's actually asked, and that is to write a differential equation down. So we're told that the rate of decrease is constant. So actually, it's going to be it's a decrease, which means the gradient, which generally is when it's positive, it's an increase. So we're going to put a negative here, and it's going to be some sort of constant. Now, actually, we can work out that constant because I've got my two coordinates. So this is 10 and 125. So the gradient is going to be 125 minus 160 divided by 10 minus 0. It's going to be minus 35 over 10, which is going to be minus 3.5. Did check, and you get the answer, the mark for this one here, but at some point you're gonna have to work out what k is. So I've just done it straight away. Part 2, solve the differential equation. Okay, so we can do this by just integrating with respect to t. It's going to give minus 3.5t plus c. We can substitute in one of the coordinates now. It makes sense to substitute in 160 because that's actually just going to give c straight away. And therefore theta is equal to 160 minus 3.5t. And then one limitation of this model, so it's going to continue to decrease indefinitely. Sorry, not increase, decrease. And it's going to go below the freezing point of water. It's going to go below absolute zero, which is not realistic because it should be settling at room temperature eventually. Right, but it is a nice sort of, one of the most, well, the most simple model you could absolutely have if it reduces at constant rate. So you can see the limitation, and that's why we're discussing it. So it's a, yeah, really nice start to this question. Part B moves us on to a revised and more realistic model. Just want to say that we've still got t is 0, theta is 160, and t is 10, theta is 125. These are two important conditions that we need. So now the rate of decrease is proportional to the difference, right, this is a bit technical, difference between the temperature of the cake and the temperature of the room. Okay, write down a differential equation. So we can say that d theta by dt is proportional. the difference between the temperature of the cake, which is theta, and the room, which is 20. So the temperature of the cake is going to be larger, so it's going to be theta minus 20. And that means that d theta by dt is going to be a constant multiplied by theta minus 20. Because again, that's what happens with proportionality. Now, because it's decreasing, we can again stick a negative in. If you forget about the negative, it's not the end of the world. You'll get a negative value for k, but it shows a bit of insight if you can do this. If it's increasing, you just put a k there. If you know it's decreasing, you put a minus there because you're ready, like you're basically showing, yeah, this is going to be um, a positive constant k. So that is actually my answer for part one. Now we've got to solve it to find theta in terms of t. Okay. Right, well, first up, we've got theta on the right-hand side, whereas we can't just integrate this directly because you need t on the right-hand side. So this is a separation of variables question. And to separate the variables, we can divide through. We have to divide through by theta minus 20. You can't multiply out the bracket and then start subtracting things because we have to be multiplying d theta by dt by the function of theta. Because the general formula is along the lines of like g of y dy by dx is equal to f of x. That is your separation of variables idea, because then we integrate both sides with respect to x. So that's what I'm going to do here, but I'm going to integrate with respect to t. Okay, and this bit becomes d theta. So I get ln of theta minus 20. Okay, that is the integral of 1 over theta minus 20. If you differentiate it back, you'll see you get the same thing. You can use a chain rule. I've basically sort of used a reverse chain rule here. And that is going to equal minus kt plus c. Right, that means I can get rid of the log straight away. I think rather than try and work out c and k from here, I'm gonna rearrange it first. It's up to you, but I think remember we're trying to get theta in terms of k and c, so it just makes a bit more sense, I think. This is going to become e to the minus k t plus c. Notice the constant is now in the power. It's very, very important. And we can write that. This is a sort of standard way you deal with this sort of situation. Because I can look at this and like, through practice you can get there. We can see that it's proportional to theta, or if it's proportional to, like, if you get minus theta in there. So if it's a positive constant, so I'm just jumping ahead a little bit, but if it's a positive constant, then you get an exponential that looks like this. It just keeps growing, like when bacteria are doubling every minute or whatever. And then if you get a negative, you get an exponential decrease. So I know it's going to be something like an exponential decrease. I've just got this minus 20, which makes it a little bit different. I know I'm going to get a negative exponential out of it. So once you know that, this is just like the standard way that you deal with it. E to the minus kt times e to the c, which I'm now going to label as a new constant. So define as, let's call it capital A. So that means theta is going to be A times e to the minus kt plus 20. All right, I'm pretty happy with that. I've just got to work out what A and K are. So remember, when t equals 0, theta equals 160. So 160 is going to equal A e to the 0, which is just 1, plus 20. So A is 140. Nice. So theta is 140 e to the minus kt plus 20. And then we've got 10 and 125. minus 10k. So 105 is going to equal this 140. I can divide by the 140. And then ln of 105 over 140 is going to equal minus 10k, from which I can work out k. Now the answer's actually left it exact, and this is a model, so I didn't leave it exact. So it's positive 0.02876. So I left my answer, and this was accepted, by the way, to leave it to three significant figures, 140 times e to the minus 0.0288 times t plus 20. This is a great model for temperature decrease because let's just sketch it out. We're starting at 120. We've got this exponential decrease going on, but it doesn't go to zero. It actually is going to tend towards room temperature, which is actually what happens, much more realistic than just decreasing indefinitely. Finally, part C says the cake is to be decorated when the temperature is 25 degrees. Find the difference in time between when the two models predict it can be decorated. So model 1, that was what we did in part A. Remember, it was theta equals 160 minus 3.5 t. So I can set theta equal to 25. And t, I can minus 160, that's going to be minus 135, and divide by minus 3.5. The double negative is going to leave me with this. I get 38.57. Then model 2. That was our one that we just found here. I really like the fact that this question's made us look into two different models, because that's actually what science is all about. You make a model and then you have to refine it. You see that time and time again in the history of science. Technically, I'm going to use the full thing. So now I can set 25 equal to that. So I can minus 20, change that just to 5. I can divide through by 140. I can take logs. So ln of 5 over 140. Yeah, and then I'm going to divide by minus 0.028. I mean, that level of accuracy is not important. I'm going to get 115.86. Again, I'm nearly there. Just got to work out the difference in time. So obviously the first model, just this linear decrease, quite quick, took 38 or 39 minutes. The other one with the exponential decrease goes it goes down quickly, but it sort of flattens off as we go along. It takes a lot longer to get to 25 degrees Celsius. So the difference, it's just going to be, I'm going to write down that I'm subtracting them. $77.29, which, is around 77 minutes. All right, and that is not far off how things do cool, this second model. So really nice question. Hope you enjoyed it. Yeah, that is it. Well done.